Hi everybody, this is Mr. Folly, and welcome to podcast 1.3. We're going to balance nuclear equations, we're going to look at nuclear reactions, we're going to talk about alpha, beta, gamma emission, electron capture, positron emission, and the band of stability. So let's go ahead and do that. Nuclear reactions. Two conditions must be met to balance a nuclear equation. 1. The conservation of mass number, which is the top number, the conservation of nuclear charge, which is the atomic number, the bottom number. Remember, if I had something that was x100 over 50, oh, come on, write for me, over 50, the top number is the mass number, and the bottom number is the number of protons. So notice here we've got 232 equals 228 plus 4. The top number is matched up. The bottom number, 90, equals 88 plus 2. So see how that happens with all nuclear equations, and this is what it's going to look like. So that's pretty much it. Oh, there's one more. Oh, no, don't do that. There's one more thing. Is every once in a while you get something like this with 3 neutrons, and a neutron has a mass of 1, but no protons. This 3 right here would mean I have 3 on top. So 3 plus 239 equals 242. Well, come on, write for me. And 238 plus 4 is 232. Alpha decay is the first type we're going to talk about. It's an alpha particle. An alpha particle is a helium nucleus. Remember, helium is 4 over 2. Now, if it's a nucleus, it's going to be plus 2 because it doesn't have any electrons. It's big, heavy, and positive. Because it's big, skin can block it. Okay. So if polonium undergoes nuclear decay, undergoes alpha decay, that means I'm going to have an alpha particle plus 2. Okay, so 4 plus something equals 209. That's 205. Something plus 2 equals 84. That's 82. And 82, when I go to my periodic table, number 82 is Pb. Beta decay. Beta emission is 0, negative 1, E. Now this negative, so I'm going to write it 0, negative 1, E. And that negative sign there just to emphasize it's negative. Or it's 0, negative 1, beta. What I forgot here is the other sign for alpha is this, 4 over 2 alpha. I might be the only one on Earth that includes the plus 2 on it, but I just like to emphasize the charges. Whoa, give me back to beta. Beta is a radioactive nucleus that undergoes beta emission. Has a neutron converted into a proton and an electron. So remember how neutrons are neutral? Right? They have a mass of 1, but they have no charge. Do you see how it could split into a positive thing and a negative thing? Well, that would be your proton and your electron. Okay. But then it spits out the electron. For example, tritium, a radioactive isotope of hydrogen, undergoes beta decay. 3 over 1 H. If it does beta decay, decay means my product is going to be a beta particle. Now I have to use the top numbers. 3 equals 0 plus 3. And then something minus 1 equals 1. So that means it would be 2 minus 1 is 1, right? Negative 1 plus 2 is 1. And I look at my periodic table. What's number 2? That's helium. Okay. These are higher E. E is energy, but can be blocked by a sheet of plastic or metal. I'm going to add or plywood. Nah. Or plywood. Plywood is just a sheet of wood you can buy at Home Depot. Okay. Gamma emission. Gamma emission looks like this. I like to show there's no other symbol for gamma. I like to put the zeros on it sometimes. The nucleus is too high of an energy and releases energy. So I think of it as if Uncle Ed has eaten too much, he needs to release energy, he lets out a belch, if you're lucky. So he's still Uncle Ed. It doesn't change the identity, it just releases energy. Energy is massless, and so is gamma. Hey, that's the mass. That's why it's 0. There's not much change for our purposes. It is chargeless and high energy, but it takes feet of lead to block it. Cerium-141 undergoes gamma radiation. So cerium is Ce. That dash 141 tells me the mass. Now I need to find cerium on my periodic table. And I don't know where it is. Oh, no, that's cesium. How do I not know where cerium is? Oh, there it is. Cerium is number 58. And if it undergoes gamma, it just does a belch. So notice if it's a belch, it's still going to be the same thing. Uncle Ed, after he belches, is still Uncle Ed. Electron capture. An inner electron gets the nucleus and joins the proton to make a neutron. This causes protons to go down and the neutrons to go up. So let's say I have rubidium 90. So rubidium 90, I did that wrong. Oh no, that's right. Rubidium 90, rubidium's number 37, and it undergoes electron capture. 0, -1 e. Okay. So what happens here? My new product, 90 plus 0 is 90. 37 minus 1 is 36. I wish I could write neater. Okay. 37 minus 1 is 36. 90 plus 0 is 90. Element with number 36 is krypton. Okay. So you can identify this as electron capture. It's the only one that's going to be on the left. Okay. Positron emission. An anti-electron, which is a positron, is ejected. So if I had to make one up, let's just say I've got polonium 210. Polonium 210. Now, polonium from the periodic table is 84, and it does positron emission. Positron emission is 0, +1 e. Plus, well, 210 equals 0 plus something, 210. Come on, handwriting, you can do it. And then something plus 1 equals 84. Hey, that's 83. Number 83 is bismuth. Okay. And then that's pretty much positron emission. The band of stability. Atoms are stable with the right ratio of protons to neutrons. Notice this is neutrons and this is protons. Remember I said Z is protons? Atoms do different types of decay to get back on the band of stability. So this is your happy spot. Whee! If you're not there, you're trying to go there. So if I plot my protons and neutrons and I'm here, I want to get to that spot. Okay? So if I do this, right here, this is the beta region, right? And then anything bigger than 83 is alpha. Okay? But that one right there is beta because beta will add protons. This right here will be positron emission or electron capture. So if I give you that graph, you should be able to do that. All right, 83 is the magic number. 83 and bigger does alpha all the time because it's just too big. So if you're too big, alpha is the biggest change. So that will get you back to the band of stability faster. Okay, beta will add protons. Positron and electron capture will remove protons. An isotope with a high neutron to proton ratio is deficient. To convert it, the neutrons to protons undergoes beta decay. Notice how that's what this says. Elements with atomic number greater than 83 undergo alpha decay. Hey. Oops. That's what this one says. Gamma cannot be predicted due to the neutron to proton ratio. Strong force. In the nucleus, some mass is converted into energy through E equals mc squared. That's called the Einstein equation. You've probably heard of that one. This is called the strong nuclear force. C is the speed of light, and the Latin word for light is celerity, or swiftness squared. So what this means is the speed of light is 3e8 meters per second. So that's a big number. That's 3, 1, 2, 3, 4, 5, 6, 7. Maybe 3 with 1, 2, yeah, 8. 1, 2, 3, 4, 5, 6, 7, 8. Bad spacing for me. But then you square that, so the number is going to be huge. So if the energy is that squared, whatever the mass is, it'll still be pretty big, right? Review. Know all the types of radiation symbol, charge, and Berthin method. Well, Berthin method isn't quite as important, so I'll go not much. But you should be able to identify it. Ah, come back. I lost it. A 1-to-1 proton-neutron ratio of calcium. Well, actually, that one I'm going to even get rid of. Bam! How about that? 83 and over is radioactive, so they're disappearing. Where did these disappearing atoms come from? They came from old Earth and the Big Bang. And I will say this to your Big Bang, and that Big Bang would be doodles in under 10.